Modern data centers are built on zero-trust architectures, defined by dense east-west traffic and complex hybrid cloud dependencies. Security teams manage this complexity with a massive array of telemetry and enforcement tools. They have the data, and they have the controls, yet threats still move laterally across workloads with high success rates. The core challenge in these environments has shifted. The primary operational failure is no longer a missed detection. It is an unsafe response. During a fast-moving incident, acting too late or applying a narrow policy allows an adversary to leak past the initial point of entry and pivot into adjacent service tiers. Conversely, acting too broadly to stop that spread can trigger a self-inflicted production outage by shutting down entire network segments unnecessarily. Data centers currently lack a reliable method to determine the mathematically minimum safe containment action required to stop a threat while preserving service availability. PTCP Quarantine version 8.2 provides a specific solution to this containment gap. It is not a firewall, and it is not a packet-level network detection sensor. It functions as a topology risk and safe containment decision layer. The service translates high-dimensional data center telemetry into precise mathematical instructions for your existing security stack. It calculates exactly where to isolate an anomaly and determines what your firewalls can safely execute without exceeding an operational safety envelope. To solve for containment, PTCP first moves past traditional layer diagrams. It models the entire data center as a quantifiable network graph. The engine ingests raw infrastructure telemetry, bandwidth, queuing, jitter, packet loss, and trust data, and applies it directly to the graph's edges. PTCP normalizes these disparate metrics into dimensionless variables, allowing the system to calculate different types of telemetry within a single mathematical framework. This turns network links into capacity-bearing bonds, representing the infrastructure as a dynamic map of available flow. Links with low trust or high packet loss are mathematically treated as longer, more costly paths for data to travel. By converting scalar counters into graph capacity and length, the engine creates a live structural map of network health, ready for diagnostic stress testing. Instead of relying on traditional alerts, PTCP evaluates regions using the D-topo composite score. D-topo identifies security-relevant graph deformation, structural changes to the network rather than isolated performance symptoms. The first driver is the median anomaly intensity within a specific region. The second is graph curvature discontinuity. This represents the physical warping of the local network shape as it reacts to the pressure of an attack or misconfiguration. The final variable measures cut capacity deviation, the current capacity of the region's boundary compared against a rolling baseline of normal behavior. These three drivers are synthesized into a single operational score that defines the health of the monitored region. Crossing thresholds transitions the region from normal to suspicious. If defective, the system provides mathematical proof detailing why the area requires immediate precision containment. Once a region is defective, the goal is to isolate the threat without destroying the availability of adjacent services. PTCP computes a minimum quarantine cut rather than a blanket segment-level block. It uses the Boykov-Kolmogorov algorithm to analyze the perimeter. The algorithm identifies the specific candidate edges, forming the thinnest logical connection between the defective region and the data center. This generates a quarantine blueprint. By severing only these connections, the threat is isolated while the graph remains untouched. This surgical approach contrasts with the traditional method of blocking an entire VLAN, which often causes more disruption than the threat itself. The minimum cut methodology turns incident containment into a mathematically minimal operation. However, a perfect mathematical cut must adhere to enterprise safety protocols to be actionable. The safe envelope governor acts as a mandatory decision gateway. Every recommended action is projected through this governance layer before any instructions are rendered. The governor evaluates the proposed cut against strict thresholds, the total blast radius, the maximum number of simultaneous actions, and allowed output formats. A closed-loop verification check ensures that no residual leakage will exist after the isolation is applied, confirming the containment will be complete. Operators choose the level of automation that fits their environment, using shadow mode for analysis, approval mode for manual review, or bounded active mode. PTCP defaults to dry run and evidence-first payloads. The automation is designed to inform the decision path, not to act as an uncontrolled change authority. The safe envelope ensures that every algorithmic recommendation becomes a governed, human-approvable change ticket that preserves operational safety. PTCP Quarantine version 8.2 is designed to sit above the existing security stack. It does not replace your firewalls, microsegmentation platforms, or NAC tools. Instead, it renders governed action plans through the enforcement systems you already use. The engine produces staged payloads, such as 40 SOAR variables or 40 manager action packages, that can be reviewed and executed by your existing orchestration and management tools. By providing the decision logic that existing enforcement tools lack, PTTCP supplies your security stack with surgical, mathematically justified action packages. In government and regulated sectors, security teams need to know exactly why a change was made. These environments cannot tolerate black box automation modifying firewalls. PTTCP's design is evidence-ready, persisting job states, capturing approval decisions, and generating the SBOM and control map metadata required for auditability. The system uses HMAC verifiable operations and blocks uncontrolled cloud remediation by default, ensuring all containment remains deterministic and auditable. In a zero-trust data center, protection requires more than static perimeters. It requires continuous, topology-aware mathematics that contain risk with surgical, auditable precision.